All right, so jumping into functions and graphing as we're going to be in for the next several weeks here, starting with absolute value function in 2.1. So essential question we want to be able to answer is, what are the features of an absolute value equation that help you graph? So an absolute value is written as bar x bar, so those vertical bars there denote absolute value, represents the distance between x and 0 on a number line. So as a distance, absolute value is always non-negative, which means it's always positive, or it can be 0. For every point on a number line except 0, that's where we get just 0, there's a point on the opposite side of 0 that is the same distance from 0. So 5 and negative 5 are 5 units away from 0. That's why we get these two statements here. Okay, so to graph these now, we're going to start by using a table. So negative 4, that comes out to be 4. Negative 2 comes out to be positive 2. 0 is 0. 2 is positive 2 still, and 4 becomes 4. So then we get seeing how those work out. We get negative 4 absolute value, which becomes positive 4. We get negative 2. This works out to be positive 2. Absolute value of 0 becomes 0. Absolute value of positive 2 is just positive 2. And the absolute value of 4 is just positive 4. So as we go to graph this, we get negative 4, positive 4. We get negative 2, positive 2. We get 0, 0, 2, 2, and 4, 4. And we get a graph that looks something like that, where those are straight lines. So we can see, similar to a linear graph where we get straight lines, but you can see we have this part down here, what we call the vertex, where we definitely change and go the other direction. All right, number 2. So now using our table, we're going to graph the function y equals absolute value of x plus 2. So as we do that, same deal, but now we got a little extra work. So I'm going to have the absolute value of negative 4, and then I'm going to plus 2. So that becomes positive 4 plus 2, which is now positive 6. We get negative 2. Absolute value plus 2. That becomes a positive 2 plus 2, which is 4. We get absolute value of 0 plus 2, which is 0 plus 2, which is just 2. And then absolute value of positive 2 is still positive 2. And we get 4. And then 4 becomes 6. So as we go to graph this, we get negative 4 and 6 is a little off our target. We get negative 2, which is 4. We get 0 and 2, 2 and 4, and 4 and 6. And then we get our graph. That again looks something like that. All right, number 3, same deal, but now we are going to be subtracting inside this. So then we get negative 4 minus 3, which becomes the absolute value of negative 7, which becomes positive 7. -2 minus 3. That becomes opposite value of -5, which is then +5. We get 0 minus 3. It becomes opposite value of -3, which is 3. Then we get 2 minus 3, which is a -1, which becomes +1. And then we get opposite value of 4 minus 3, which becomes +1, which equals 1. So as we go to graph this one, we get -4, which is 7, which is way off our charts up here. We get -2, which is 5, just a little bit off. We get 0, which is 3. We get 2, which is 1. And we get 4, which is 1. So as we can see here, we kind of have this line, and we're not sure where we turn around and go, but I will tell you it's going to be at that point right there. All right. So a question that I want you to reflect on is, what changed from graph of 1 to the graphs of 2 and 3? So as we saw in graph 2, as we added a value to it, it moved it up. And then as we subtracted within our absolute value, it actually moved it to the right. It went to the opposite direction. So what we want to do here on number 4 is, without using a table, graph the function y equals x plus 1 plus 3. So we want to look at and fill in some of these characteristics over here. And this is really what's going to end up mattering for us to graph it. So our vertex, as we saw, it is the opposite of that value there. So it's going to be at -1. And then that 3 stays positive. So our vertex is at -1, 3. Our axis of symmetry is x equals our x coordinate of our vertex, so x equals -1. Concavity is how it opens up or down. Right now, since this is positive, we're going to open up. And then our horizontal shift is, we went left 1, and vertical shift, we went up 3. Now our domain, since we're not falling in under the 3 main deals, or 2 main deals, there's not a fraction, which we can't have 0 in the denominator, and there's not a radical, so we don't have to worry about negatives being under the radical. So then this would be all reals, which I'm going to write over here as all reals as a reminder. But the way we're going to end up writing it is in interval notation, so -infinity to +infinity, or in inequality, we go from -infinity is less than x, which is less than +infinity. And then our range, okay, is our possible y values. And so we look at this graph. This is our vertex. Our graph is going to open up. Right now we have a slope of 1. I'll talk a little bit more about on the next problem. But our graph is going to look something like that. So then our range would go from our bottom, which is at 3, and we're going to include that 3. That's why it's a closed bracket. And that's going to go to +infinity, or we can write it as 3 less than or equal to, because we need to include that 3. Now this time it is y, and then we're less than. It's going to go on forever to +infinity. Now a couple reminders on this. So domain is our possible x values. Range is possible y values. The parenthesis is open, so it's like less than or greater than. The bracket is called a closed bracket. That's because it's closed. And that's a less than or equal to or greater than or equal to symbol there. All right, let's look at number 5 now. Okay, same deal. We're looking at our vertex. So our vertex on this one, so inside the parentheses is x minus 3, so we're going to go opposite. So it's going to be a positive 3, and then outside of it, you see that there's nothing here, so that is 0. Our axis of symmetry is x equals 3. So let me plot 3, 0. Now concavity, as you look here, we have a negative. So that means we're going to be concave down. And so we have a horizontal shift of right 3. Vertical shift, since our vertex y value is at 0, is none. Our domain, again, no issues, no fractions, no radicals. So we're all reals, and I'm going to write it as negative infinity to positive infinity. And then our range, this time we're negative, we're concave down, so it's going to start here and go down. Now I need to fix what that graph looks like. But that now starts at negative infinity because we start from the bottom and work our way up. So we go from negative infinity and then we top out at 0, and we're going to include that. If we're going to write that as an inequality, we'd write it as y is less than or equal to 0. Our range would be negative infinity less than x less than positive infinity. Now over here, we have an addition to our graph that we haven't talked about yet. We have this 1/2. So that 1/2 right in front, it's like our slope on a linear equation, because essentially these are two linear equations that we have going here. So 1/2, so we're going to go down 1 and over 2, down 1 and over 2, and that then gives us what our graph looks like. So that would be that graph there with a 1/2 and a negative concave graph. All right, little reflection. What effect did the negative 1/2 on the graph of the function? Let's go ahead and answer that, and we'll discuss that when we come back into class. All right, so let's talk about the general equation. So given the function y equals a x minus h plus k, so our vertex is going to be h comma k. Notice the h is the opposite sign of that. And just like we saw in previous problems, we always took the opposite sign inside the opposite value there. So that's positive h and k. Our axis of symmetry is x equals h, our x coordinate of our vertex. Our concavity is based on a. If a is greater than 0, so it's positive, we are concave up. And if a is less than 0, so a is negative, we are concave down. The actual numeric value doesn't matter, just whether it's positive or negative. Our horizontal shift comes from our h. Our vertical shift comes from the k. Our domain for this is going to be all reals. There is no restriction, so we get negative infinity to positive infinity. Our range now comes from our k value and our a, our concavity. Whether it opens up or down. Now, last thing is we're going to have to write equations given a graph. So what we want to identify is our h and k. So as we look at this, our h and k comes from our vertex, so that's going to be this point right here. So our h is -4. Our k is at -2. And then our a, we just got to check our slope. And as we go, we're just going to count our slope. So we go up 1, over 1. So our a value is 1, and our graph is opening up. We're concave up, so that's going to be a positive. So then to write our equation, we have y equals our a value. So our a value is 1, and then absolute value of x minus our h, which is a -4. And then our k, which is a -2. So to simplify that, we get y equals 1, which we don't have to write. X, two negatives make a positive, 4 minus 2. All right, and number 9, our h. There is no shift, so our h is at 0. Our k, we shifted vertically 3. Our a is going to be negative because our graph is going down. And then now we have to check, so I go down 1, 2, and then over 1 to get to the next lattice point. So that's going to be 2 over 1, which is just 2. So then our equation becomes y equals our a, which is -2, x minus our h, which is 0, and then plus k, which is 3. So we get y equals 2, absolute value of x, plus 3. All right, so our essential question, what are the features of an absolute value equation that help you graph? So go ahead and jot down, look back at what the characteristics are, and identify those and be able to answer that question. At your homework, which will be in class, we'll do it as a class, and it is going to be a worksheet, and so you will be getting that the next class period.